first team to present today in the finals of the 2016 Rice Business Plan Competition. Please help me welcome MDAR Technologies from Northwestern University.
Hello, Houston. We're MDAR. I'm Jesse Chang, co-founder and CEO of MDAR Technologies. I'm also JD MBA at Northwestern. Here at MDAR, we help robots see in the wild. This is Google's self-driving car. It's really cool, right? A lot of you have probably heard about it. That's driven over 1 million miles with only one little fender bender. But what you probably don't know is that those 1 million miles have been in perfect weather. That self-driving car has a really difficult time seeing in conditions like snow, fog, and rain. And it's not just that. Objects in motion, bright sunlight, and highly reflective surfaces are all very challenging for the self-driving car to see. And it's not just self-driving cars. Any kind of vision system, precision agriculture, industrial robotics, or even pipeline inspection, or helping a spacecraft dock, are all very challenging for existing 3D vision systems. And that's why, ladies and gentlemen, we created MDAR. Ta-da! So, MDAR is able to simultaneously achieve very high resolution at real-time speeds while being uncompromised by its environment. More than that, we've been able to build a portfolio of patents around our technology. We filed for PCT protection on the underlying technology, and we've recently applied for 2 more patents that are defensive as well. Lastly, our technology is so compelling that Google has given us an unrestricted grant to develop our technology. Now I'm going to hand it over to my team. Mark is going to explain to you how our technology works, while Alex and Chris will tell you how we're going to take it to market. And I'll take it all back at the end. So with that, I hand it over to Mark.
Thank you, Jesse. So before I explain how MDAR works, I want to spend a few seconds on just thinking about what does 3D vision actually mean. So if you take your phone and you take a picture, you take a 2D image of the environment. With this 2D image, you can tell what the scene looks like, but you can't tell how far things are away. This is 3-dimensional information. You need to be able to tell how far an obstacle is away for a robot for it to be able to avoid it. A 3D sensor gives a robot the capability to do so. My background is in building lightweight robots. I work with BMW's advanced R&D group in Munich. These lightweight robots help workers along the assembly line. One of the most challenging things that we have encountered there was finding a vision system that can function in all the different conditions that you have. You have very bright surfaces, you have shiny surfaces. And there's a number of different technologies on the market that you could use for 3D scanning, but they don't produce the results that we wanted. The most accurate one that you can think of is laser scanning. Laser scanning works by looking at the scene with a camera and projecting onto the scene with a laser projector. This gives you a very high resolution result, so the 3D data is very, very accurate. It's very slow though, and this is why. So you have your camera, you take a picture, and then in that picture, you process it on a computer, and you look for that one line in the scene. By looking at how deformed the line is, or where you see it in the image, you can tell how far away the object is that the line is bouncing off. The problem with this approach is that you're actually wasting over 99% of the data. That means while you're looking for that one line, you don't care about the rest of the scene. As you do that over and over and over and over, as the laser moves across the scene, this process is extremely slow. At the same time, as I mentioned earlier, it's very accurate. So in an ideal world, what we want to do is we want to build a laser scanner that is very fast. And this, ladies and gentlemen, is precisely what MDAR is. MDAR is a technology, it's the laser scanner that we're having around there, that uses a specialized camera, a motion contrast camera, combined with a laser projector. This enables us to do laser scanning at video frame rates, which is a novelty for 3D sensors. Now, how exactly does that work? A motion contrast camera enables us to only capture that 1% of the data that we actually need to do the 3D reconstruction of the scene. This means that the rest of the picture that I was showing earlier, the 99%, we don't even capture that. And this is not software, this is hardware, this is on the chip level itself. The sensor only fires, pixels only fire if it's the data that we're looking for. So this enables a number of different features for our technology. We can perform very well in all these conditions that Jesse mentioned earlier. To illustrate this a little bit better, I would like to take a moment and invite everyone to take an educated guess what you see here. What you see here is a very challenging scene as looked through by our competition. It's really hard to tell what it is, right? Even as a human. If you look at the same scene through our sensor, you might have a better idea now what it is. Exactly. It's a light bulb that's turned on. You can see here the comparison between MDAR and the current market leader in 3D scanning. Everything that's black in the competition is information that we don't have, where if the robot had to make a decision based on this information, it wouldn't be able to. Now, why do we care about a light bulb? Turns out being able to scan a light bulb directly translates to being able to see in bright light. And that's really important. Otherwise, you failed quite dramatically. But it's not just bright light. Our technology, when compared to existing technologies, excels in all these different categories. Basically, we combine the best things of laser scanning, LiDARs, stereo, and structured light and put it together into MDAR. And that's why MDAR is able to outperform all these systems. Now we have the technology, and I'm going to hand it over to Alex now, who's going to explain to you how we take it to market.
Thank you, Mark. So now that you understand a little better how our technology works, we'd like to talk you through the markets that we're targeting and how we're going to go after them. As Jesse mentioned before, our technology solves problems in a wide range of industries, but in particular, self-driving cars and industrial automation. So back to Google's self-driving car. That KFC bucket on top is their existing LiDAR vision system. It's not only an eyesore, it also costs $70,000. On top of that, the image resolution is not very high, and it performs poorly in bad weather. Contrast that with the MDAR technology. Our unit costs today on our prototype are just $5,000, a significant cost advantage in addition to the improvements we offer in resolution and resilience. Industrial automakers today are producing around 100 million cars a year. With projected adoption rates of self-driving cars, combined with the expected cost of these vision sister systems, we estimate this will be a $15 billion market opportunity by 2020. That's just for the vision systems alone. As self-driving car adoption rates continue to grow, this will be a $40 billion market opportunity by 2025. So let's take a closer look at the market. It's constructed of essentially three constituents: suppliers, integrators, and OEMs. MDAR is playing the role of a supplier, selling directly to OEMs with autonomous vehicle programs such as Tesla and Toyota, or indirectly via integrators such as Delphi and Google. It's important to note that Google is not a competitor, but rather a customer. They're interested in using their best-in-class software technology combined with world-class hardware to make autonomous vehicles a reality. We acknowledge that the solution will likely be a combination of these technologies, but given our superior performance, we know that MDAR will be a critical piece. I'll now turn it over to Chris to tell you a little bit more about industrial automation.
Thanks, Alex. So there are a wide variety of potential applications in industrial automation. To give you an example, though, we'll give you one that we heard from an aerospace engineer that was talking to us. This guy was looking at bird strikes. So this is when a bird strikes the wing of an aircraft at high speed while in flight. This not only does damage to the bird, but also the wing of the aircraft. The dents these cause can actually increase fuel use by thousands of dollars on a single flight. So this company was looking to find a way to spot those dents right after a plane landed. They developed a series of drones and rovers to fly around the aircraft to spot the dents. Unfortunately, the program stalled. They could not find a sensor that was able to see past the bright sunlight and reflections coming off the wings. There is no sensor that can do this today. Now, this may seem like a very specific example, and it is, but there's literally hundreds of thousands of other ones just like it. This is a $6 billion industry today, and this is just looking at the actual vision systems alone. It's growing to $11 billion by 2020. Now, much of that growth is driven by robotics. They're becoming smaller, more nimble, more collaborative, coming off the assembly line and working closer with human beings. To make this happen, though, they need to see the way that you and I do, and we give them a better set of eyes that they can swap in. Looking at the industry today, again, it looks kind of like self-driving cars. We're a vision supplier selling through a set of integrators. In this case, though, these integrators are actually responsible for installing and customizing these systems, putting them onto assembly lines and other robotics applications. These wide set of integrators let us reach a diverse set of end industries, everything from electronics to heavy manufacturing. This is an incumbent industry, so there are players out there today doing it, but they're very focused on the 2D space, more basic applications like quality control. We're targeting the 3D space. We're looking at robotic guidance, more sophisticated outdoor inspection applications. These applications today are underserved because of the limitations of today's technologies. This is also where most of the growth is expected to come in the robotics industry, and we have a huge advantage going forward. I'm now going to pass it off to Jesse, who's going to talk about some long-term markets and how we're going to deliver.
Why, thank you, Chris. So, Chris and Alex here have all told you about some very exciting opportunities inside of the automotive industries and industrial automation industries. Now I'm here to tell you about how our solution cuts across a multitude of industries. The emerging augmented reality markets are projected to become a $20 billion market, a $10 billion market by 2020. Currently today, they're using it in places like the International Space Station, ISS, where they're helping astronauts see better in 3D. Soon that technology is going to come down to Earth, where it will fundamentally change the way man and machine interact. Hopefully we can get MDAR up there too someday. Next, back down on here on Earth, there are clear and obvious defense applications. Things such as tracking an RPG when it's coming out of Humvee, or helping a Black Hawk helicopter land in brownout conditions. There's also some very compelling lawnmower consumer-facing applications. For instance, imagine you're enjoying the sun by your Texas poolside, while your lawnmower autonomously mows the lawn by itself. And your butler bot is bringing you an ice-cold beer. Isn't America great? I love America. So, we have a lot of very attractive markets. How do we prioritize these? Well, I'll tell you how. First, we're going to enter into the industrial automation market. Why? Because it's an existing market today where there's already demand. We've already been talking with several OEMs and integrators that want our technology today. Next, as production increases and price falls, we'll eventually be able to enter our long-term target, which is self-driving cars. Make no mistake, self-driving cars are our eventual target. Eventually, as we move further along production and price continues to fall even more, we'll be able to opportunistically enter into markets like augmented reality. So, more specifically, our beachhead is going to be industrial automation because, as we discussed earlier, it's a real market today, and also there's a high willingness to pay given the high ROI in industrial automation. As, again, price continues to fall, we'll be able to enter into self-driving cars, where while margins are lower, volume is much higher. On the hardware side, we're going to be selling to integrators and also directly to OEMs. We are already in contact and have traction with these integrators and OEMs. We also have been discussing with automotive OEMs as well how we might work on self-driving car projects together. In fact, these are all the people that we have been talking to. Each and every one of our conversations with all of these people ends the exact same way. They always ask us, when can we get our hands on an MDAR? Why? It's because the fact that current technologies just don't solve the problems that they're facing. All the different examples my colleagues mentioned earlier, and many, many more. And that's why, ladies and gentlemen, we're here today. With $1 million from you, and another $1.5 million that we're applying for through SBIR grants, we hope to take our product from what you see here and what you've been touching to our final product. There are some milestones we must hit first. For instance, getting into a commercial beta that we can put into the hands of people like Google, BMW, and Caterpillar to test and iterate our product until we move on to full production. And so that's one of our major milestones. Until then, very first, we're going to have to continue to modify our MEMS module. What that means, quite simply, is we're just going to be swapping out the LED with a laser. And then there's just pure engineering sweat after that. Circuit board design, packaging it, putting it inside a metal casing instead of the 3D printed box that we used to make the prototype that you guys have been handing around. So, this is a team that's going to make it all happen. You have myself, I'm a JD MBA at Kellogg and Northwestern Law. My background is in venture capital, where I invested in companies exactly like MDAR. My co-founder, Nathan Matsuda, is the inventor of this technology and a PhD candidate at Northwestern. He wishes he could be here, but his wife is 9 months pregnant. He's also, interesting trivia fact, a Primetime Emmy nominee during his prior career as a visual effects artist. Professor Ali Koser, another co-inventor of the technology, he was actually here at Rice University as a visiting professor just last quarter. He's also the director of the Computational Photography Lab at Northwestern University. Mark Ngashi, our resident prodigy, who was a robotics engineer at BMW, will be supporting Nathan and Nolly. And lastly, we have Chris and Alex, our two MBA extraordinaires who will be helping us take this to market. Chris's background is in management consulting, where he worked at the Boston Consulting Group. and Alex Wern has PM experience at places like IBM and Adobe. So, to recap, we have a best-in-class product. Our technology cuts across a multitude of industries and solves problems no other technology can do today. It addresses markets that are primed for explosive growth. Today, they represent a $7 billion opportunity. In 4 short years, they represent a $20 to $25 billion market opportunity, which is why we need to act now. Third, we have protected our technology by filing for PCT applications so that we have global protection, and we've also applied for 2 more provisional patents around various processes related to our technology. Lastly, we have a rockstar team ready to execute on this vision. Thank you very much, ladies and gentlemen. We're MDAR, and we have robots in the car.
Any questions? If you guys will put your hand up, the mics will come around. Yep. And there's a mic over here. Put your hand up and so you can get teed up for the next question afterwards.
Good presentation. What are the top 3 technical risks and what's your plan to retire them?
So the very first step that we are working on is customizing basically this MEMS module. And then going forward, basically, for example, for industrial automation, there is certain certifications that we'll have to comply with. And then as we move from the industrial applications to self-driving cars, we'll make modifications to the module necessary there too. So those are basically the 3 steps. Does that answer your question?
Wasn't that, I was wondering a little bit deeper, but that's okay.
Yes.
Yeah, could you tell us a bit more about the technology, specifically the difference with the motion contrast camera? My initial impression is that if you're in a moving vehicle, everything around you will be moving. So how can you limit the data acquisition to just, how are you not doing what other people are doing, collecting all data?
Oh, so you mean because the camera is moving that you're capturing the... No, so the fact is that you're only looking at the laser, right? And the laser is in a different spectrum. So...
Right, but I mean, other companies are already doing laser scanning and presumably their focus.
But, yeah, exactly. But then still, if you do laser scanning, the dynamic range of your camera is different. Because here we're only triggering on and off events if we see the differential event on the pixel. So basically, if you do conventional laser scanning, you use a standard camera and you put a filter in front of it. Here, this camera uses this differential approach on the individual pixels, enabling us to have a much higher dynamic range. And then because it's an invisible spectrum, there's no problem with the movement of the camera.
To your point about the moving car, though, the motion of the car will be very slow relative to the motion of the laser itself. This is scanning across 1 million points per second. Relative to that, any motion of the car is small. And like we said, there's filtering, so we're actually only looking at the laser itself.
Tim, here you go.
So with that impressive slide where you're talking about logos, we all recognize, they say, when can we get our hands on it, when can we test it? Those companies, will they be looking at buying a finished good from you and incorporating it in their product? Or are they going to prefer licensing technology for you so they can control their finished product better?
I would say it depends on the customer. So most of the more industrial OEM types are used to having multiple different suppliers coming in. So they would want to buy, in the industrial space, it's a box, right? The integrator is going to buy a box and install it on the assembly line. The auto space, it's going to be, a set of components that, again, are going to go into the, kind of by the headlights of the car. More consumer side, they might actually prefer to license, given the small form factor of the product and how they want to break it down. So one of the optics companies that we're talking with, it's actually the redacted one on the page, is interested in licensing as well. So depends on the customer.
Yeah. Next questions and looking for hands up. All right, Art.
Does this work underwater?
Does it work underwater?
So we haven't tested it. On purpose?
It's not waterproof right
It's
now.
not waterproof right now.
Please don't put it in water.
But yes, so there are interesting applications also, especially in scattered media, which then directly translates to underwater applications too.
So is that a yes, but you don't have
Well, being a scientist,
I think so,
we haven't
yeah,
tested
tested.
it properly underwater. So pretty hard to explain.
Do all of you plan to stay with the company after you graduate?
Yes, so right now the status is the core engineering team will continue working on this while Chris and Alex and Jesse are graduating this year, and they will be supporting the business development side. But the next steps really are really like sweat engineering work and getting us to the commercial data. And so these people that are working on the engineering team are, yes.
Benjamin?
Over here. How does your product deal with rain?
That's a very good question. So, for example, I mean, you're probably getting at the advantages, for example, compared to LiDAR. LiDAR is very, very low resolution. And as a matter of fact, you have like 64 points, that's your resolution. On this, we have much, much higher resolution, means we can sample the scene much faster. And then, because of that, we can basically detect when you're hitting a raindrop, for example, versus when you're not. Because you're sampling the same point so often, and you have a much higher resolution, which basically enables you to see rain, or at least a little bit better than the competition.
And will the sensor need to be on top of the car? And will there only be one sensor in a car, or will there be four?
So we'll probably end up, depending on the car, it will not be on top, but I think we can all say that looks pretty bad. Once we've done a little bit more miniaturization, right now there's a lot of other stuff inside our box. It's going to be two pieces of that. You've got a little module that's about the size of a postage stamp that does a laser. You've got an image sensor also about the size of a quarter. So that will not be in a big box on top. It'll be integrated. We imagine there'll probably be at least two on the front because there's about a 80-degree field of view. So they probably look something like this. Maybe one on the back. They might go with something cheaper, maybe like a point LiDAR, depending on how good of a view they want behind them. But given how good of an image we have in front, we think there'll be multiple.
So, have you explored using other wavelengths other than LiDAR?
That's a great question.
Yeah, so in research, going through the different iterations of the prototypes, we've used a multitude of lasers, different powers, different wavelengths. In the current setup that we have, we're using visible light because that's the projection module that we modified. But then going forward, especially also to increase range, we'll have to use a different wavelength.
What major milestones will you accomplish with the 1 billion, and what does the next financing requirement look like, and how long will that first $1 million take you?
Sure. So in terms of the milestones, the first $1 million really gets us to that commercial beta, right? So that's the activities that Jesse talked around modifying this MEMS module that does the projection, as well as all the packaging, the software interfaces that would be needed for the full industrial product. So that gets us to commercial beta, which then gets us to the next round of financing.
Right. So as we take it into full production, obviously we're going to need to do a larger Series A round. So hopefully at that point we'll be looking at doing a $6 million round, and that will also finance development or begin the development of self-driving car beta as well.
Yeah, so Ben, Tesla seems to have solved the autopiloting problem pretty handily. And so how's your technology better or cheaper than what they're doing? And if you fast forward to the point at which your product is available for autopiloting cars, how would you compare your technology to the eventual improvement of where Tesla will be?
So Tesla is taking a very software-heavy approach to autonomous cars, right? And software can get you pretty far, but the problem is, and that's also what you saw with the picture of the light bulb, even if you have the best software, if the data that you're collecting is not good, it will fail, right? And if you're driving the car, you don't want the car to be able to fail. So there will always be a combination of different sensors. There will be cameras on the car, so Tesla is going a very camera-heavy approach with a lot of software, but it requires a certain, basically also like a three-dimensional sensor that not just gives you an image, but also three-dimensional data. And out of those, ours is the only one that can perform in all these conditions. So I think by the time that happens, this will be an integral part for any kind of autonomous system, especially also self-driving cars.
Yeah, one last question.
So you mentioned Quanergy, or they were in your slide, and you talked about the high cost of LiDAR, but my understanding is that Quanergy is hoping to drive the cost of LiDAR down to like $150 or $200. So what happens, how much will your product cost, and what happens when they succeed at that?
So for starters, the $250 price target they laid out, that is a long-term price target they put out. They didn't say when they're going to hit it, and we're a little skeptical given the advances they need to make in optical phaser arrays. So they're relying on a whole new, fairly untested type of technology to steer the beam. If they get there, we can actually use that technology to replace our MEMS. In the meantime, we're going to stick with MEMS because it's much cheaper, and we are planning to reach under $500 for the auto market in coming years.
All right, time's up. How about applause? Thanks for the team.